So for part A, so part A, the sketch that corresponds to the scenario would be from A right here, because it starts to compress, negative A max, and then it goes down to the origin point, all the way to A max. So this is because of Hooke's law. Negative Kx is because the force of the spring points opposite of the direction it's going. This explains why it's like this. And then for part B, basically, it starts off at negative A, and it goes to here. This is one full period. This is one full period. This is 2 cycles. And for velocity, since x is cosine, velocity has to be sine, because if it starts out at A, that means v is 0. And so since it starts off at negative A goes into positive, or the speed has to go positive direction for it to go right. So we'll go up here and back down. And this is one full cycle. And repeat. 2 full cycles. And then for acceleration, it's the opposite of the x. So it would be mirrored but opposite. So this would be your acceleration of the 2 cycles right here. And for C, I would agree with the statement that that the V would double, because if you use conservation of energy, Ka squared equals 1/2 mv squared, or V max squared. The 2's cancel out, and you divide m over, cancel out this m, and you square root both sides to cancel this x, or the square on this V max. So you get V equals a square root of k over m, because this square in this a right here cancels out due to the square root. You can take that out. And since we double the a, V max, to a square root k m, and since the force of the spring doesn't change because it's constant, and the mass doesn't change, but the a does, and it's not square root or anything, it does double the V max. So I would agree. And for D, frequency doesn't rely on amplitude or the displacement or the distance, because in this function 1/2 pi square root k it relies on the constant, k constant, and the mass. But since the mass hasn't changed, that means the frequency doesn't change. So the frequency stays the same. So I disagree with their statement that it quadruples. So for E, I would use conservation of energy for this. So I would use 1/2 Ka squared equals 1/2 mv squared plus 1/2 kx squared. So the 2's would cancel out. So you're left with Ka squared equals mv squared plus kx squared. And so you would subtract this kx squared over to the other side, and you're left with Ka squared minus kx squared equals mv squared. And so you could take out the common or the like terms, and then you get a squared minus x squared equals to mv squared. And you can divide m by both sides, and you're left with v squared equals k over m a squared minus x squared. And since we know that km actually just equals to the omega squared equals km, we could substitute this km as omega squared. So we get v squared equals omega squared parentheses a squared minus x squared. And so we could square root this on both sides, and we're left with v equals omega square root of a squared minus x squared. And this proves the function given right here that you can calculate velocity with this equation. This turns into plus or minus because of the square root. That is the answer. So for F, basically in the first scenario, the rough surface, we know that this block, since it's approaching equilibrium, we know that the spring force is pointing to the right, and our FK is pointing to the left because it is opposite. And so for the next one, our spring force is pointing to the left because it needs to push it to the left for it to slow down to reach A max, and then if it needs to get pushed backwards for opposite. So by that, Fs should be pointing to the left because it passes equilibrium, and then our Fk still points to the left because of friction. So these would be our diagrams for a spring before equilibrium, and then a spring past equilibrium. With the rough surface. That's what we would have right here. And our Fs would be obviously bigger, because if the Fk was bigger, the Fk would be pulling it towards that way. So that's why Fs is bigger. So part G asks needs us to label the two scenarios and label it on a x to t graph for both scenarios, and be 2 pi t, and and we know that since we have a compressed spring is at negative 2a, and one is at negative a, one is at a, and one is at 2a. So we know that for scenario 1, we start off at negative a, and then we will move up negative a and move up to here because it reaches equilibrium. It goes up and then back down, or back down to this a, not this g, and then back down to negative a as one cycle, and then it would do the same thing right here. And then for the negative 2a spring, or the spring compressed to negative 2a, starts from right here, and it will end off at equilibrium right here as well. As for one cycle, reaches to 2a up here, and then back down to this 0, and then back to negative 2a for one cycle. And then we'll do the same thing up here. And come back down. And this would be our graph, X and T graph for both scenarios. And this is scenario 2. And this is scenario 1. Scenario 1, where it starts off at negative A, and scenario 2 starts as compressed at negative 2A. So this is what our graph would look like for X and T graph. So for part H, determine the ratio of T. So we know that our T3M would equal to 2 pi square root M over K, or 3M over K, correct? And then our Tm would just equal to 2 pi square root M over K. And so if we put this over each other, our K's just cancel, our M's cancel, our pi's cancel, so we're just left with square root 3 over 1. And the square root of 3 is equal to 1.73. This is our ratio for that. T3M over Tm. So for part I, we know that we could use moment of inertia here. So basically, if we know that mv max equals to the new m, which is 3mv via vf, we know that our masses cancel, and then we just divided 3 over. So our new vf would equals to v max over 3. So we know that our new vf is less than the old v max, or our new v is less than the old v. So since we know this, we can then use conservation of energy, where we know that we actually lose energy due to the mass, or due to the velocity decreasing due to the momentum of the block dropping onto the block on the spring. So this would be 1/2 3m, and then our new v, which is v over 3 squared. And then we know that we just square root, so v squared equals 9, 3m over 1/2. And so the 3's could just divide these two, so we're left with 1/2 m v squared over 3, and we take that out, so we get 1/3 1/2 mv squared. And then since we know that the PE of the spring is always the same still, so we could just make that equal to, so our so it'd be 1/2 Ka squared. This is our conservation of energy we can use here, and then we cancel out the 2's, and then we get Ka squared equals 1/3 mv squared, and then we would just divide this by k and square root the whole thing. So we're left with A equals V square root 1/3 or M over 3K. And if we go back to this function, conservation energy without the block dropping onto it, we get 1/2 mv squared. These two cancel. And then K A squared equals mv squared. Then you divide K, and then square root, and you're left with A equals V square root M over K. So we know that since we're dividing it by a greater number, we're actually we know that the A will actually be smaller because we have a smaller denominator. So yeah, so these two equations right here prove that A3M is less than AM due to the momentum, or because it was an inelastic collision, and because we know that since we use conservation of energy, we lose energy through the process. So we plug that back into the formula here, or to conservation of energy, and then we found that is actually less than AM due to the denominator being divided by a bigger number.